Stanford University.
All right. Hello, everybody. Welcome to lecture 7, or maybe it's 8. Definitely today is sort of the beginning of where we talk about models that really matter in practice. We'll talk today about the simplest recurrent neural network model one can think of. But in general, this model family is what most people now use in real production settings. So it's really exciting. We only have a little bit of math in between, and a lot of it is quite applied and should be quite fun. Just one organizational item before we get started. I'll have an extra office hour today right after class. I'll be again on Q status 68 or so. Last week, we had to end at 8:30, and there's still a lot of people who had a question. So I'll be here after class for probably like another 2 hours or so, try to get through everybody's questions. Are there any questions around projects and organizational stuff? All right, then let's take a look at the overview for today. So to really appreciate the power of recurrent neural networks, it makes sense to get a little bit of background on traditional language models, which will have huge RAM requirements and won't be quite feasible in their best kinds of settings where they obtain the highest accuracies. And then we'll motivate recurrent neural networks with language modeling. It's a very important kind of fundamental task in NLP that tries to predict the next word, something that sounds quite simple, but is really powerful. And then we'll dive a little bit into the problems that you can actually quite easily understand once you have figured out how to take gradients and you actually understand sort of what backpropagation does. And then we can go and see how to extend these models and apply them to real sequence tasks that people really run in practice. All right, so let's dive right in. Language models. So basically, we want to just compute the probability of an entire sequence of words. And you might say, well, why is that useful? Why should we be able to compute how likely a sequence is? And actually comes up for a lot of different kinds of problems. So one, for instance, in machine translation, you might have a bunch of potential translations that a system gives you, and then you might want to understand which order of words is the best. So the cat is small should get a higher probability than small the is cat. But based on another language that you translate from, it might not be as obvious, and the other language might have a reverse word order and whatnot. Another one is when you do speech recognition, for instance. It also comes up in machine translation a little bit, where you might have, well, this particular example is clearly more a machine translation example, but comes up also in speech recognition, where you might want to understand which word might be the better choice given the rest of the sequence. So walking home after school sounds a lot more natural than walking house after school, but home and house have the same translation or the same word in German, for instance, which is just house, H-A-U-S, and you want to know which one is the better one for that translation. So it comes up in a lot of different kinds of areas. Now, basically, it's hard to compute the perfect probabilities for all potential sequences because there are a lot of them. And so what we usually end up doing is we basically condition on just a window. We try to predict the next word based on just the previous n words before the one that we're trying to predict. So this is, of course, an incorrect assumption. The next word that I will utter will depend on many words in the past. But it's something that had to be done to use traditional count-based machine learning models. So basically, we'll approximate this overall sequence probability here with just a simpler version. In the perfect sense, this would basically be the product here of each word given all preceding words from the first one all the way to the one just before the ith one. But in practice, this probability with traditional machine learning models we couldn't really compute, so we actually approximate that with some number of n words just before each word. So this is a simple Markov assumption, just assuming the next action or next word that is uttered just depends on n previous words. And now, if we wanted to use traditional methods, that are just basically based on the counts of words and not using any of our fancy word vectors and so on, then the way we would compute and estimate these probabilities is essentially just by counting how often does, if we want to get the probability for the second word given the first word, we'll just basically count up how often do these two words co-occur in this order, divided by how often the first word appears in the whole corpus. Let's say we have a very large corpus and we just collect all these counts. And now if we wanted to condition not just on the first and the previous word, but on the two previous words, then we'd have to compute all these counts. And now you can kind of sense that, well, if we want to ideally condition on as many n-grams as possibly before, but we have a large vocabulary of, say, 100,000 words, then we'll have a lot of counts. Essentially, 100,000 cubed, many numbers we would have to store to estimate all these probabilities. Does that make sense? Are there any questions for these traditional methods? All right, now, the problem with that is that the performance usually improves as we have more and more of these counts, but also you now increase your RAM requirements. And so one of the best models of this traditional type actually required 140 gigs of RAM for just computing all these counts when they wanted to compute them for 126 billion token kind of corpus. So it's very, very inefficient in terms of RAM, and you would never be able to put a model that basically takes up, stores all these different n-gram counts. You could never store it in a phone or any small machine. And now, of course, once computer scientists struggle with a problem like that, they'll find ways to deal with it. And so there are a lot of different ways you can back off. You say, well, if I don't find the 4 gram or I didn't store it because it was not frequent enough, then maybe I'll try the 3 gram. And if I can't find that or I don't have many counts for that, then I can back off and estimate my probabilities with fewer and fewer words in the context size. But in general, you want to have at least sort of 3 or 4 grams that you store, and the RAM requirements for those are very large. So that is actually something that you'll observe in a lot of comparisons between deep learning models and traditional NLP models that are based on just counting words for specific classes. The more powerful your models are, sometimes the RAM requirements can get very large very quickly, and there are a lot of different ways people try to combat these issues. Now, our way will be to use recurrent neural networks, where basically they're similar to the normal neural networks that we've seen already, but they will actually tie the weights between different time steps. And as you go over it, you keep reusing essentially the same linear plus nonlinearity layer. And that will, at least in theory, allow us to actually condition what we're trying to predict on all the previous words. And now here, the RAM requirements will only scale with the number of words, not with the length of the sequence that we might want to condition on. So now, how is this really defined? Again, you'll see different kinds of visualizations, and I'm introducing you to a couple. I like sort of this unfolded one, where we have here a abstract hidden time step t, and it's conditioned on ht minus 1, and then here you compute ht plus 1. But in general, the equations here are quite intuitive. We assume we have a list of word vectors. For now, let's assume the word vectors are fixed. Later on, we can actually loosen that assumption and get rid of it. And now, at each time step, to compute the hidden state, at that time step, we'll essentially just have these two matrices, these two linear layers, matrix vector products, and we sum them up. And that's essentially similar to saying we concatenate ht minus 1 and the word vector at time step t, and we also concatenate these two matrices. And then we apply an element-wise linearity. So this is essentially just a standard single-layer neural network. And then on top of that, we can use this as a feature vector or as our input to our standard softmax classification layer to get an output probability, for instance, over all the words. So now the way we would write this out in this formulation is basically the probability that the next word is of this specific, at this specific index j, conditioned on all the previous words, is essentially the jth element of this large output vector. Yes? What is S? So here, you can have different ways to define your matrices. Some people just use U, V, and W or something like that. But here, we basically use the superscript to just identify which matrix we have. And these are all different matrices. So WHH, the reason we call it HH is it's the W that computes the hidden layer H given the input HT-1. And then you have an HX here, which essentially maps X into the same vector space that we have our hidden states in. And then S is just our softmax W, the weights of the softmax classifier. And so let's look at the dimensions here. It's, again, very important. Oh, I have another question. Oh, so why do we concatenate and not add is the question. So they're the same. So when you write WH, let's use the same notation, plus WHX times X, then this is actually the same thing. And so this will now basically be a vector. And we have here the nonlinearity, but it doesn't really change things. So let's just look at this inside part here. Now, if we concatenated H and X together, we now have, and let's say X here has a certain dimensionality, which we'll call D. So X is in RD, and our H will define to be in, for having the dimensionality RDH. Now, what would the dimensionality be if we concatenated these two matrices? So we have here the output has to be, again, a DH matrix. And now this vector here is a, what dimensionality does this vector have when we concatenate the two? That's right. So this is a D plus DH times 1. And here we have a DH times what matrix? Has to be the same dimensionality, so D plus DH. And that's why we could essentially concatenate here WH in this way and WHX here. And now we could basically multiply these. And if you, again, if this is confusing, you can write out all the indices. And you realize that these two are exactly the same. Does that make sense? Right? So as you sum up all the values here, they'll essentially just get summed up. Also, it doesn't matter if you do it in one go or not. So this is really just a single layer neural network where you concatenated two inputs. But it's in many cases for recurrent neural networks, it's written this way. All right. So now here are two other ways you'll often see these visualized. This is kind of a not unrolled version of a recurrent neural network. And sometimes you'll also see sort of this self loop here. I actually find these kinds of unrolled versions the most intuitive. All right, now when you start any kind, oh, yep. Oh, good question. So what is X bracket T? It's essentially the word vector for the word that appears at the Tth time step. It's as opposed to X sub T. And intuitively here, X sub T, you could define it in any way. It's really just like as you go through the lectures, you'll actually observe different versions. But intuitively here, X sub T is just a vector at Xt. But here, xt is really an input, and what it means in practice is you actually have to now go at that tth time step, find the word identity, and then pull that word vector from your glove or word2vec vectors and get that in there. So x sub t we used in previous lectures as the tth element, for instance, in the whole embedding matrix, all our word vectors. So this is just to make it very explicit that we look up the identity of the word at the tth time step and then get the word vector for that identity, like the cat vector in all our word vectors. Yeah. So I'm showing here a single layer neural network at each time step, and then the question is whether that is standard or just for simplicity. It is actually the simplest and still somewhat useful variant of a recurrent neural network, though we'll see a lot of extensions even in this class, and then in a lecture next week we'll go to even better versions of these kinds of recurrent neural networks. But this is actually a somewhat practical neural network, though we can improve it in many ways. Now, you might be curious when you just start your sequence, and this is h0 here, and there isn't any previous word, what you would do. And the simplest thing is you just initialize the vector for the first hidden layer at the first or the 0th time step as just a vector of all zeros. Right, and this is the xt definition here I just described. It's the column vector of L, which is our embedding matrix at index t, which is the time step t. All right, so it's very important to keep track properly of all our dimensionality. Here, WS, the softmax, actually goes over the size of our vocabulary, V times the hidden state. So the output here is the same as a vector of the length of the number of words that we might want to be able to predict. All right, any questions for the feed-forward definition of a recurrent neural network? All right, so how do we train this? Well, fortunately, we can use all the same machinery we've already introduced and carefully derived. So basically here we have probability distribution over the vocabulary, and we're going to use the same exact cross-entropy loss function that we had before, but now the classes are essentially just the next word. So this actually sometimes creates a little confusion on the nomenclature that we have, because now technically this is unsupervised in the sense that you just give it raw text. But this is the same kind of objective function we use when we have supervised training, where we have a specific class that we're trying to predict, right? So the class at each time step is just the word index of the next word. And you're already familiar with that. Here we're just summing over the entire vocabulary for each of the elements of y. And now, in theory, you could just, to evaluate how well you can predict the next word over many different words and longer sequences, you could, in theory, just take this negative of the average log probabilities over this entire data set. But for maybe historical reasons and also reasons like information theory and so on that we don't have to get into, what's more common is actually to use perplexity. So that's just 2 to the power of this value, and hence we want to basically be less perplexed. So the lower our perplexity is, the less the model is perplexed or confused about what the next word is. And we essentially, ideally, will assign a higher probability to the word that actually appears in a longer sequence at each time step. Yes? Any reason why 2 to the j? Yes, but like, well, it's sort of a rat hole we can go down, maybe after class, like just information theory, bits, and so on. It's not necessary. All right. All right, so now you would think, well, this is pretty simple, right? We have a single set of W matrices, and training should be relatively straightforward. Sadly, And this is really the main drawback of this and a reason of why we introduce all these other more powerful recurrent neural network models. Training these kinds of models is actually incredibly hard. And we can now analyze using the tools of backpropagation and chain rule and all of that. And we can analyze and understand why that is. So basically, we're multiplying here the same matrix at each time step, right? So you can kind of think of this matrix multiplication as amplifying certain patterns over and over again at every single time step. And so in a perfect world, we would want the inputs from many time steps ago to actually be able to still modify what we're trying to predict at a much later time step. And so one thing I would like to encourage you to do is to try to take the derivatives with respect to these W's if you just had a 2 or 3 word sequence. It's a great exercise, great preparation for the midterm, and it'll give you some interesting insights. Now, as we multiply the same matrix at each time step moving forward prop, we have to do the same thing during backpropagation. And so we have, remember, our deltas, our error signals, and sort of the global elements of the gradients. They will essentially at each time step flow through this network backwards. So when we take our cross entropy loss here, we take the derivatives, we backpropagate, we compute our deltas. Now, the first time step here that just happened close to that output will make a very good update. And we'll probably also make a good update to the word vector here if we wanted to update those. We'll talk about that later. But then as you go backwards in time, what actually will happen is your signal might get either too weak or too strong. And that is essentially called the vanishing gradient problem. As you go backwards through time and you try to send the error signal at time step t many time steps into the past, you'll have the vanishing gradient problem. So what does that mean and how does it happen? Let's define here a simpler but similar recurrent neural network that will allow us to give you an intuition and simplify the math downstream. So here we essentially just say, all right, instead of our original definition where we had some kind of f, some kind of nonlinearity, here we use the sigma function. You could use other ones. Chris introduced the rectified linear units and so on. Instead of applying it here, we'll apply it in the definition just right in here. So it's the same thing. And then let's assume for now we don't have the softmax. We just have here a standard sort of a bunch of unnormalized scores, which just really doesn't matter for the math, but it'll simplify the math. Now, if you want to compute the total error with respect to an entire sequence, with respect to your W, then you basically have to sum up all the errors at all the time steps, right? At each time step, we have an error of how incorrect we were about predicting the next word. And that's basically the sum here. And now we're going to look at the element at the tth time step of that sum. So let's just look at a single time step, a single error at a single time step. And now even computing that will require us to have a very large chain rule application, because essentially this error at time step t will depend on all the previous time steps too. So you have here the delta or det over dyt, so the the hidden state, the softmax output, or here these unnormalized score output yt. But then you have to multiply that with a partial derivative of yt with respect to the hidden state. So that's just this guy right here, or this guy for ht. But now that one depends on, of course, the previous one, right? This one here, but it also depends on that one and the one before that, and so on. So that's why you have to sum over all the time step from the first one all the way to the current one where you're trying to predict the next word. And now each of these was also computed with a w, so you have to multiply partial of that as well. Now let's dig into this a little bit more. And you don't have to worry too much if this is like a little fast. You won't have to really go through all of this, but it's very similar to a lot of the math that we've done before, so you can kind of feel comfortable for the most part going over it at this speed. So now remember here our definition of ht. We basically have all these partials of all the HTs with respect to the previous time steps, the H's of the previous time steps. Now, to compute each of these, we'll have to use the chain rule again. And now what this means is essentially a partial derivative of a vector with respect to another vector. Something that, if we're clever about our backprop definitions before, we never actually have to do in practice, right? Because this is a very large matrix, and we're combining the computation with the flow graph and our delta messages before, such that we don't actually have to compute explicitly these Jacobians. But for the analysis of the math here, we'll basically look at all the derivatives. So just because we haven't defined it, what's the partial for each of these is essentially called a Jacobian, where you have all the partial derivatives with respect to each element of the top here, HT, with respect to the bottom. And so in general, if you have a vector valued function output and a vector valued input, and you take the partials here, you get this large matrix of all the partial derivatives with respect to all outputs. Any questions? All right, so basically here, a lot of chain rule, and now we got this beast, which is essentially a matrix, and we multiply for each partial here, we actually have to multiply all of these, right? So this is a large product of a lot of these Jacobians. Now, we can try to simplify this and just say, all right, let's say there's an upper bound, and we also, the derivative of h with respect to hj, actually, with this simple definition of each h, actually can be computed this way, and now we can essentially upper bound the norm of this matrix with the multiplication of basically these this equation right here, where we have wt, and if you remember our backprop equations, you'll see some common terms here, but we'll actually write this out as not just an element-wise product, but we can write the same thing as a diagonal, where we have, instead of the element-wise elements, we basically just put them into the diagonal of a larger matrix, and we zero pad everything that is off diagonal. Now, we have these two, we multiply these two norms here. Now we just define beta, w and beta h, as essentially the upper bounds, some number, single scalar for each, as like how large they could maximally be, right? We have w, we can compute easily any kind of norm for our w, right? It's just a matrix, compute a matrix norm, get a single number out. And now, basically, when we write this all, we put all these together, then we see that an upper bound for these Jacobians is essentially, for each one of these elements, is this product. And if we define each of the elements here in terms of their upper bounds beta, then we basically have this product beta here taken to the t minus kth power. And so as the sequence gets longer and longer and t gets larger and larger, it really depends on the value of beta to have this either blow up or get very, very small, right? If now the norms of this matrix, for instance, that norm, and you have control over that norm, right? You initialize your weight matrix W with some small random values initially before you start training. If you initialize this to a matrix that has a norm that is larger than 1, then at each backpropagation step, and the longer the time sequence goes, you basically will get a gradient that is going to explode, because you take some value that's larger than 1 to a large power here. Let's say you have 100 or something, and your norm is just 2, then you have 2 to the 100 as an upper bound for that gradient. And vice versa, if you initialize your matrix W in the beginning to a bunch of small random values such that the norm of your W is actually smaller than 1, then the final gradient that will be sent from ht to hk could become a very, very small number, right? You have like a half to the power of 100. Basically, none of the errors will arrive. None of the error signal will get smaller and smaller as you go further and further backwards in time. So if the gradient here is exploding, does that mean a word that is further away has a bigger impact on the word that's closer? And the answer is, when it's exploding like that, you'll get to not a number in no time. Like it doesn't even become a practical issue because the numbers will literally become not a number because it's too large a value to compute, and we'll have to think of ways to combat. It turns out the exploding gradient problem has some really great hacks that make them easier to deal with than the vanishing gradient problem. And we'll get to those in a second. All right, so now you might say this could be a problem. Now, why is the vanishing gradient problem an actual problem in practice? And again, it basically prevents us from allowing a word that appears very much in the past to have any influence on what we're trying to predict in terms of the next word. And so here are a couple of examples from just language modeling where that is a real problem. So let's say, for instance, you have Jane walked into the room, John walked in too, it was late in the day, Jane said hi too. Now you can essentially put an almost probability mass of 1 that the next word in this blank is John, right? But if now each of these words had a word vector, you pipe it into a hidden state, you compute this, and now you want the model to pick up the pattern that if somebody met somebody else and all this complex stuff, and then they said hi too, and the next thing is a name, you want to put a very high probability on it, but you can't get your model to actually send that error signal way back over here to now modify the hidden state in a way that would allow you to give John a high probability. And really, this is a large problem in any kind of time sequence that you have. And many people might intuitively say, well, language is mostly a sequence problem, right? You have words that appear from left to right or in some temporal order as we speak. And so this is a huge problem. And now we'll have a little bit of code that we can look into. But before that, we'll have the awesome Shane give us a little bit of an intermission. Right.
Hi, so let's take a short break from recurrent neural networks to talk about transition-based dependency parsing, which is exactly what you guys saw this time last week in lecture. So just as a recap, a transition-based dependency parser is a method of taking a sentence and turning it into a dependency parse tree. And you do this by looking at the state of the sentence and then predicting a transition. And you do this over and over again in a greedy fashion until you have a full transition sequence, which in self encodes the dependency parse tree for that sentence. So I want to show you how to get from the model that you'll be implementing in your assignment 2, question 2, which you're hopefully working on right now, to syntax-net. So what is syntax-net? Syntax-net is a model that Google came out with, and they claim it's the world's most accurate parser. And it's new, fast-performant TensorFlow framework for syntactic parsing. It's available in over 40 languages. The one in English is called Parsy McParseface. So my slides seem to have been jumbled a little bit here, but hopefully you can read through it. So basically, the model that our baseline we're going to begin with is the Chen and Manning model, which came out in 2014. And Chen and Manning are respectively your head TA and instructor. And the models that produce syntax-net, and there's just 2 stages of improvements, those directly modified Chen and Manning's model, which is exactly what you guys will be doing in assignment 2. And so we're going to focus today on the main bulk of these changes, modifications, which were introduced in 2015 by Weiss et al. So without further ado, I'm going to look at their 3 main contributions. So the first one is they leveraged unlabeled data using something called tri-training. The second is that they tuned their neural network and made some slight modifications. And the last and probably most important is that they added a final layer on top of the model involving a structured perceptron with beam search. And so each of these seeks to solve a problem. So the first one is tri-training. So as you know, in most supervised models, they perform better the more data that they have. And this is especially the case for dependency parsing, where as you can imagine, there are an infinite number of possible sentences with a ton of complexity, and you're never going to see all of them, and you're going to see even some of them very, very rarely. So the more data you have, the better. So what they did is they took a ton of unlabeled data and two highly performant dependency parsers that were very different from each other. And when they independently agreed on a dependency parse tree for a given sentence, then that would be added to the labeled data set. And so now you have 10 million new tokens of data that you can use in addition to what you already have. And this by itself improved a highly performant network, its performance by 1% using the unlabeled attachment score. So the problem here was not having enough data for the task, and they improved it using this. The second modification they made, or augmentation they made, was by taking the existing model, which is the one you guys are implementing, which has an input layer consisting of the word vectors, the vectors for the part of speech tags, and the arc labels, with one hidden layer and one softmax layer predicting which transition, and they changed it to this. Now, this is actually pretty much the same thing except for three small changes. The first is that there's two hidden layers instead of one hidden layer. The second is that they used a ReLU nonlinearity function instead of the cube nonlinearity function. And the third and most important is they added a perceptron layer on top of the softmax layer. And notice that the arrows that it takes in it takes in as input the outputs from all of the previous layers in the network. So this perceptron layer wants to solve one particular problem. And this problem is that greedy algorithms aren't able to really look ahead. They make short-term decisions, and as a result, they can't really recover from one incorrect decision. So what they said is, let's allow the network then to look ahead. And so we're going to have a tree which we can search over. And this tree is a tree of all the possible partial transition sequences. So each edge is a possible transition from the state that you're at. As you can imagine, even with 3 transitions, your tree is going to blossom very, very quickly, and you can't look that far ahead and explore all of the possible branches. So what you have to do is prune some branches. And for that, they use beam search. Now, beam search is only going to keep track of the top k partial transition sequences up to a depth of m. Now, how do you decide which k? You're going to use a score computed using the perceptron weights. You guys probably have a decent idea at this point of how perceptron works. And the exact function they used is shown here, and I'm going to leave up the annotations, and so you can take a look at it later if you're interested. But basically, those are the 3 things that they did to solve the problems with the previous Chen and Manning model. So in summary, Chen and Manning had a unlabeled attachment score of 92%, already phenomenal performance. And with those 3 changes, they boosted it to 94%. And then there's only 0.6% left to get you to SyntaxNet, which is Google's 2016 state-of-the-art model. And if you're curious what they did to get that 0.6%, take a look at Andor et al.'s paper, which uses global normalization instead of local normalization. So the main takeaway, and it's pretty straightforward, but I can't stress it enough, is when you're trying to improve upon an existing model, you need to identify the specific flaws that are in this model, in this case, the greedy algorithm, and solve those problems specifically. And in this case, they did that using semi-supervised method, using unlabeled data. They tuned the model better, and they used the structured perceptron with beam search. Thank you very much.
Kind of awesome. You can now look at these kinds of pictures, and you totally know what's going on. And like state-of-the-art stuff that one of the largest companies in the world publishes. Exciting times. All right. So we're going to go through a little bit of like a practical Python notebook sort of implementation that shows you a simple version of the vanishing gradient problem where we don't even have a full recurrent neural network, but we just have a simple 2-layer neural network. And even in those kinds of networks, you will see that the area that you start at the top and the norm of the gradients as you go down through your network, the norm's already getting smaller. And if you remember, these were the 2 equations where I said, if you get to the end of those 2 equations, you know all the things that you need to know, and you'll actually see these two equations in the code as well. So let's jump into this. I don't see it. Let me get out of the presentation. All right, it's better. All right, now I'll zoom in. So here we're going to define a super simple problem. This is a code that was started in 231N by Andre, and we just modified it to make it even simpler. So let's say our data set, to keep it also very simple, is just this kind of classification data set where we have basically 3 classes, the blue, yellow, and red, and they're basically in the spiral cluster form. We're going to define our simple nonlinearities. This is kind of, you can kind of see it as a solution almost to parts of the problem set, which is why we're only showing it now. We'll put this on the website too, so no worries. You can use it later. We'll basically define here f, our different nonlinearities, element-wise, and the gradients for them. So this is f and f prime if f is a sigmoid function. We'll also look at the ReLU, the other nonlinearity that's very popular. And here we just have the maximum between 0 and x. Again, very simple function. Now this is a relatively straightforward definition and implementation of a simple 3-layer neural network. It has this input, here our nonlinearity, our data x, just these points in 2-dimensional space, the class, whether it's one of those 3 classes. We'll have this model here. We have our step size for SGD and our regularization value. Now these are all our parameters, W1, W2, and W3 for all the outputs and variables of the hidden states. Two sizes bigger. All right. All right. Now, if our nonlinearity is the ReLU, then we have here ReLU, and we just have our input x, multiply it. In this case here, x can be the entirety of the data set because the data set's so small. Each mini batch, we can essentially do batch. Again, if you have realistic data sets, you wouldn't want to do full batch training, but we can get away with it here. It's a very tiny data set. We multiply W1 times x plus our bias terms, and then we have our element-wise rectified linear units, or ReLU. Then we compute hidden layer 2. Same idea, but now it's input instead of x as the previous hidden layer. And then we compute our scores this way. And then here we'll normalize our scores with the softmax. Just exponentiate our scores, sum of them, so on. Very similar to the equations that we walked through. And now it's just basically an if statement. Either we use ReLUs as our activations, or we use a sigmoid, but the math inside is the same. All right, now we're going to compute our loss. It's our good friend, the simple average cross-entropy loss plus the regularization. So here we have negative log of the probabilities. We sum them up over all the elements. And then here we have our regularization. It's the L2, standard L2 regularization, where we just basically sum up the squares of all the elements in all our parameters. And I guess it does cut off a little bit when we zoom in. But yeah, just all 3 have the same amount of regularization, and we add that to our final loss. And now every 1,000 iterations, we'll just print our loss and see what's happening. And this is something you always want to do too, always want to visualize, see what's going on. And hopefully a lot of this is now looks very familiar. Maybe you've implemented it not quite as efficiently in problem set 1, but maybe you have, and then it's very, very straightforward. Now, that was the forward propagation. We can compute our error. Now we're going to go backwards, and we're computing our delta messages first from the scores. Then we have here our back propagation, and now we have the hidden layer activations, transpose times delta messages to compute W. Again, remember we have always, for each W here, we have this outer product, and that's the outer product we see right here. And now the softmax was the same regardless of whether we used the ReLU or sigmoid. Let's walk through the sigmoid here. we now basically have our delta scores and have here the product. So this is exactly computing delta for the next layer, and that's exactly this equation here, and just Python code. And then again, we'll have our updates dw, which is again this outer product right there. So it's a very nice sort of equations code, almost a nice one-to-one mapping between the two. All right, now we're going to go through the network from the top down to the first layer. Again, here, outer product. And now we add the derivatives for our regularization. In this case, it's very simple. Just the matrices themselves times the regularization. And we combine all our gradients in this data structure. And then we update all our parameters with our step size and SGD. All right, then we can evaluate how well we do on the training set so that we can basically print out the training accuracy as we train this. All right, now we're going to initialize all the dimensionality. So we have here just our two-dimensional inputs, 3 classes. We compute our hidden sizes of the hidden vectors. Let's say they're 50. It's pretty large. And now we can run this. All right, we'll train it with both sigmoids and rectified linear units. And now, once we want to analyze what's going on, we can essentially now plot the sum of the magnitudes of the gradients. So those are essentially the updates as we do backpropagation through this network. And what we'll see here is the sum of the gradients for the first and the second layer when we use sigmoid nonlinearities. And basically here, the main takeaway message is that blue is the first layer and green is the second layer. So the second layer is closer to the softmax, closer to what we're trying to predict. And hence, its gradient is usually larger in magnitude than the one that arrives at the first layer. And now imagine you do this 100 times, right? And you have intuitively your vanishing gradient problem in recurrent neural networks. It'll essentially be 0. They're already almost halved in size over the iterations when you just had 2 layers. And the problem is a little less strong when you use rectified linear units, but even there, you're going to have some decrease as you continue to train. All right, any questions around this code snippet and vanishing gradient problems? No? Sure. It's a good question. The question is, why are the gradients flatlining? And it's essentially because the data set is so simple that you actually just perfectly fit it, your training data, and then there's not much else to do. You're basically in a local optimum, and then not much else is happening. So yeah, so these are the outputs where if we visualize the decision boundaries. Here we have the ReLU, and the ReLU you see a little bit more sort of edges because you have sort of linear parts of your decision boundary, and the sigmoid is a little smoother, a little rounder. All right. So now you can implement like a very quick version to get an intuition for the vanishing gradient problem. Now, the exploding gradient problem is in theory just as bad, but in practice, it turns out we can actually have a hack that was first introduced by Tomasz Mikolov. And it's very unmathematical in some ways, because you say, oh, you have a large gradient of 100, let's just cap it to 5. That's it. You just define a threshold, and you say whenever the value is larger than a certain value, just cut it. Totally not the right mathematical direction anymore, but turns out to work very well in practice. Yeah. So vanishing gradient problems, how would you cap it? It's like it gets smaller and smaller, and you just multiply it, but then it's like it might overshoot. It might go in the completely wrong direction. And you don't want to have the 100th word unless it really matters. It's like you can't just like make all the 100 words or 1,000 words of the past all matter the same amount, right? Intuitively, that doesn't make that much sense either. So this gradient clipping solution is actually really powerful. And then a couple of years after it was introduced, Joshua Bengio and one of his students actually gained a little bit of intuition. And it's something that I encourage you always to do too, not just in the equations where you can write out a recurrent neural network where everything is one-dimensional and the math comes out easy and you gain intuition about it. But you can also, and this is what they did here, implement a very simple recurrent neural network which just had a single hidden unit. Not very useful for anything in practice, but now with a single unit W and still the bias term, they can actually visualize exactly what the error surface looks like. So and oftentimes we call the error surface or the energy landscape or sort of the landscape of our objective function, this error surface. And basically, you can see here the size of the z-axis here is the error that you have when you train this on a very simple problem. I forgot what the problem here was, but it's something very simple like keep around this unit and remember the value and then just return that value 50 time steps later. Something simple like that. And what they essentially observed is that in this error surface or error landscape, you have these high curvature walls. And so as you do update each little line here, you can interpret as like what happens at an SGD update step. Right? You update your parameters and you say, in order to minimize my objective function right now, I'm going to change the value of my one hidden unit and my bias term just like by this amount to go over here, and all of a sudden you hit these large curvature walls, and then your gradient basically blows up and it moves you somewhere way different. And so intuitively, what happens here is if you rescale to the fixed size with this threshold method, then essentially you're not going to jump to some crazy far away place, but you're just going to stay in this general area that seemed useful before you hit that curvature wall. So the question is, intuitively, why wouldn't such a trick work for the vanishing gradient problem, but it does work for the exploding gradient problem? Why does the reason for the vanishing does not apply to the exploding gradient problem? So intuitively, this is exactly the issue here. So the exploding, as you move way too far away, you basically jump out of the area where you, in this case here, for instance, we're getting closer and closer to a local optimum, but the local optimum was very close to a high curvature wall, and without the gradient problem, without the clipping trick, you would go way far away, right? Now, in the vanishing gradient problem, it gets smaller and smaller. So in general, clipping doesn't make sense, but let's say so that's that's the obvious answer, right? You can't, if something gets smaller and smaller, it doesn't help to have a maximum and then make it cut it to that maximum, because that's not the problem, right? It goes in the opposite direction. And so that's kind of the most obvious intuitive answers. Now you could say, why couldn't you, if it gets below a certain threshold, blow it up? But then that would mean that, let's say you wanted to predict a word, and now you're 50 time steps away, and really the 51st doesn't actually impact the word you're trying to predict at time step t, right? So you're 50 time steps before, and it doesn't really modify that word, and now you're artificially going to blow up and make it more important. So that's less intuitive than saying, I don't want to jump into some completely different part of my error surface. The wall just comes from, this is what the error surface looks like for a very, very simple recurrent neural network with a very simple kind of problem that it tries to solve. And you can actually use most of the networks that you have. You can try to make them have just two parameters, and you can visualize something like this too. In fact, it's very intuitive sometimes to do that when you try different optimizers. like we'll get to those in a later lecture, like atom or SGD momentum and so on. We'll talk about those soon. You can actually always try to visualize that in some simple kind of landscape. And this just happens to be the landscape that this particular recurrent neural network problem has with one hidden unit and just a bias term. So the question is, how could we know for sure that this happens with nonlinear actions and multiple weights? So you also have some nonlinearity here in this. So that intuitively wouldn't prevent us from transferring that knowledge. Now, in general, it's very hard. We can't really visualize very high dimensional spaces. There is actually now an interesting new idea that was introduced, I think, by Ian Goodfellow, where you can actually try to, let's say you have your parameter space. Inside your parameter space, you have some kind of cost function. So you say, my W matrices are this value and so on, and I have some error when all my values are here. And then I start to optimize, and I end up somewhere here. Now, the problem is we can't visualize it because it's usually in realistic settings. These, you have 100 million, or well, at least 1 million or so parameters, sometimes 100 million. And so something crazy might be going on as you optimize between this. And so because we can't visualize it, and we can't even subsample because it's such a high-dimensional space, what they do is they actually draw a line between the point from where they started with their random initialization before optimization and the line where all the way to the point where you actually finished your optimization. And then you can evaluate along this line at a certain intervals, you can evaluate how big your error is. And if that error changes between two such intervals a lot, then that means you have very high curvature in that area. So that's one trick of how you might use this idea and gain some intuition of the curvature of the space. But yeah, only in 2 dimensions can we get such nice intuitive visualizations. Yeah. So the question is, why don't we just have less dependence? And the question is, of course, it's a legit question, but ideally, we'll let the model figure this out. Ideally, we're better at optimizing the model, and the model has, in theory, these long-range dependencies. In practice, they rarely ever do. In fact, when you implement these, and you can start playing around with this, and it's something I encourage you all to do too. As you implement your models, you can try to make it a little bit more interactive. Have some IPython notebook, give it a sequence, and look at the probability of the next word, and then give it a different sequence where you change words like 10 time steps away, and look again at the probabilities. And what you'll often observe is that after 7 words or so, the words before actually don't matter, especially not for these simple recurrent neural networks. But because this is a big problem, there are actually a lot of different kinds of solutions. And so the biggest and best one is one we'll introduce next week. But a simpler one is to use rectified linear units and to also initialize both of your W's, the ones from hidden to hidden and the ones from the input to the hidden state with the identity matrix. And this is a trick that I introduced a couple years ago, and then it was sort of combined with rectified linear units and applied to recurrent neural networks by Kwok Lit. And so the main idea here is if you move around in your space, let's say you have your H, and usually we have here our WHH times H plus WHX plus X. And let's assume for now that H and X are in the same, have the same dimensionality. So then all these are essentially square matrices. And we have here our different vectors. Now, in the standard initialization, what you would do is you just have a bunch of small random values in all the different elements of W. And what that means is as you start optimizing, whatever X is, you have some random projection into the hidden space. Instead, the idea here is we actually have identity initialization. Maybe you can scale it such that you have a half times the identity. And what does that do intuitively when you combine the hidden state and the word vector? That's exactly right. If this is an identity initialized matrix, so it's just 1, 1, 1, 1, 1, 1 on the diagonal, and you multiply all of these by 1/2, same, it's just having a half, a half, a half, and so on. And you multiply this with this vector, and you do the same thing here. What essentially that means is you have a half times that vector plus a half times that other vector. And intuitively, that means in the beginning, if you don't know anything, let's not do a crazy random projection into the middle of nowhere in our parameter space, but just average and say, well, as I move through the space, my hidden state is just kind of a moving average of the word vectors, and then I start making some updates. And it turns out when you look here and you apply this to a very toy problem of MNIST, which we don't really have to go into, but it's a bunch of small digits, and they're trying to basically predict what digit it is by going over all the pixels in a sequence, instead of sort of using other kinds of neural networks like convolutional neural networks. And basically, we look at the test accuracy. You have, these are very long time sequences, and the test accuracy for these is much, much higher when you use this identity initialization instead of random initialization, and also using rectified linear units. Now, more importantly, for real language modeling, we can compare recurrent neural networks in this simple form. So, we had the question before, like, do these actually matter, or did I just kind of describe single layer recurrent neural networks for the class to describe the concept? And here we actually have these simple recurrent neural networks, and we basically compare this one. It's called Knaster-Ney with 5 grams. So a lot of counts and some clever back-off and smoothing techniques, which we won't need to get into for the class. And we compare these on 2 different corpora, and we basically look at the perplexity. So these are all perplexity numbers. And we look at the neural network or the neural network that's combined with Knaster-Ney assumed probability estimates. And of course, when you combine the two, then you don't really get the advantage of having less RAM. So ideally, this by itself would do best. But in general, combining the two used to still work better. These are results from 5 years ago, and the field moves very quickly. I think the best results now are pure neural network language models. But basically, we can see that compared to Knaster-Ney, even back then, the neural network actually works very well and has much lower perplexity than just the Knaster-Ney or just the count-based. Now, one problem that you'll observe in a lot of cases is that the softmax is really, really large. So your word vectors are one set of parameters, but your softmax is another set of parameters. And if your hidden state is 1,000, and you'd say you have 100,000 different words, then that's 100,000 times 1,000 dimensional matrix that you have to multiply with the hidden state at every single time step. So that's not very efficient. And so one way to improve this is with a class-based word prediction, where we first try to predict some class that we can come up with. And there are different kinds of things we can do. In many cases, you can kind of sort just the words by how frequent they are, and say the 1,000 most frequent words are in the first class, the next 1,000 most frequent words are in the second class, and so on. And so you first basically classify, try to predict the class based on the history, and then you predict the word inside that class based on that class. And so this one is only 1,000 dimensional. And so you can basically do this. And now the more classes, the better the perplexity, but also the slower the speed, the less you gain from this. And especially at training time, which is what we see here, this makes a huge difference. So if you have just very few classes, you can actually reduce the number here of seconds that each epoch takes by almost 10x compared to having more classes, or even more than 10x if you have the full softmax. And even at test time, this is faster because now you only essentially evaluate the word probabilities for the classes that have very high probability here. All right, one last trick, and this is maybe obvious to some, but it wasn't obvious to others, even in the past when people published on this. but you essentially only need to do a single backwards pass through the sequence once you accumulate all the deltas from each error at each time step. So looking at this figure really quick again, here essentially you have one forward pass where you compute all the hidden states and all your errors, and then you have only a single backwards pass. And as you go backwards in time, you keep accumulating all the deltas at each time step. And so originally people said, oh, for this time step, I'm going to go all the way back. And then I'm going to go to the next time step, and then I go all the way back. And then go to the next step, and all the way back, which is really inefficient and is essentially same as combining just all the deltas in one clean back propagation step. And again, it kind of is intuitive, an intuitive sort of implementation trick, but people gave that the term back propagation through time. All right, now that we have these simple recurrent neural networks, we can use them for a lot of fun applications. In fact, the named entity recognition that we used an example with the window, in the window model, you could only condition the probability of this being a location, a person, or an organization based on the words in that window. With the recurrent neural network, you can, in theory, take and condition these probabilities on a lot larger context sizes. And so you can do named entity recognition. You can do entity level sentiment and context. So for instance, you can say, I like the acting, but the plot was a little thin. And you can say, like, I want to now, for acting, say positive, and predict the positive class for that word, predict the null class, not a sentiment for all the other words, and then plot should get a negative class label. Or you can classify opinionated expressions, and this is what Ozan Irzoy did in Claire Cardi at Cornell, where they essentially used recurrent neural networks for opinion mining, and essentially wanted to classify whether each word in a relatively small corpus here is either a direct subjective expression or an expressive subjective expression. So either direct or expressive. So basically, these DSEs or direct subjective expressions explicitly mention some private state or speech event, whereas the ESEs just indicate the sentiment or emotion without explicitly stating or conveying them. So here's an example, like the committee, as usual, has refused to make any statements. And so you want to classify as usual as an ESE and basically give each of these words here a certain label. And this is something you'll actually observe a lot in sequence tagging tasks. Again, all the same model. It's a recurrent neural network. You have a softmax at every time step. But now the softmax actually has a set of classes that indicate whether a certain expression begins or ends. And so here, you basically have this BIO notation scheme where you have the beginning or the end or a null token. It's not any of the expressions that I care about. So here you would say, for instance, as usual is an overall ESE expression. So it begins here, and it's in the middle right here. And then these are neither ESEs or DSEs. All right, now they started with the standard recurrent neural network, and I want you to, at some point, glance over these, be able to glance over these equations and just say, oh, I've seen this before. It doesn't have to be W superscript HH and so on, but whenever you see the summation order, of course, doesn't matter either. But here they use W, V, and U, and then they defined, instead of writing out softmax, they write G here. But when you look at these equations, I hope that eventually you're just like, oh, it's just a recurrent neural network, right? You have here your hidden to hidden matrix, you have your input to hidden matrix, and here you have your softmax weights U. So same idea, but these are the actual equations from this real paper that you can now kind of read and immediately sort of have the intuition of what happens. All right, now this is a unidirectional recurrent neural network where if we try to make the prediction here of whether this is an ESE or whatever, named entity recognition, really any kind of sequence labeling task, what's the problem with this kind of model? What do you think, as we go from left to right only, what do you think could be a problem for making the most accurate predictions? That's right. Words that come after the current word can't be helping us to make accurate predictions at that time step, right? Because we only went from left to right. And so one of the most common extensions of recurrent neural networks is actually to do bidirectional recurrent neural networks, where instead of just going from left to right, we also go from right to left. And it's essentially the exact same model. In fact, you could implement it by changing your input and just reversing all the words of your input, and then it's exactly the same thing. And now, here's the reason why they don't have superscripts with WHH, because now they have these arrows that indicate whether you're going from left to right or from right to left. And now, they basically have this concatenation here, and in order to make a prediction at a certain time step t, they essentially concatenate the hidden states from both the left direction and the right direction. And those are now the feature vectors. And this vector ht coming from the left has all the context, or again, 7+ words, depending on how well you train your RNN, from all the words on the left. Ht from the right has all the context from the words on the right. And that is now your feature vector to make an accurate prediction at a certain time step. Any questions around bidirectional recurrent neural networks? You'll see these a lot in all the recent papers in deep learning in various modifications. Yeah? Have people tried convolutional neural networks? They have, and we'll actually mention, we have a special lecture also where we'll talk a little bit about convolutional neural networks. Yeah. So you don't necessarily have a cycle, right? You just go, you basically, as you implement this, you go once all the way through the left, and you don't have any interactions with the step that goes from the right. You can compute your feed forward HTs here for that direction are only coming from the left. And the HT from the other directions you can complete, in fact, you could parallelize this if you want to be super efficient and have one core implement the left direction, one core implement the right direction. So in that sense, it doesn't make the vanishing gradient problem worse. But of course, just like any recurrent neural network, it does have the vanishing gradient problem and the exploding gradient problems, and it has to be clever about clipping it and so on. Yeah. We call them standard feed-forward neural networks or window-based feed-forward neural networks. And now we have recurrent neural networks. And this is really one of the most powerful family. And we'll see lots of extensions. In fact, if there's no other question, we can go even deeper. It is, after all, deep learning. And so now you'll observe why we definitely had to skip that superscript. And we have different characters here for each of our matrices. Because instead of just going from left to right, you can also have a deep neural network at each time step. And so now, to compute the ith layer at a given time step, you essentially, again, have only the things coming from the left that modify it, but you don't just take in the vector from the left, you also take the vector from below. So in the simplest definition, that is just your x, your input vector, right? But as you go deeper, you now also have the previous hidden layers input. Yeah. Instead of, why are the So the question is, why do we feed the hidden layer into another hidden layer instead of the y? In fact, you can actually have so-called short circuit connections too, where each of these h's can go directly to the y as well. And so here, in this figure, you see that only the top ones go into the y, but you can actually have short circuit connections where y here has as input not just ht from the top layer, noted here as capital L, but a concatenation of all the h's. It's just another way to make this monster even more monstrous. And in fact, there are a lot of modifications. In fact, Shane has a paper on arXiv right now on a search space, Odyssey, type thing where you have so many different kinds of knobs that you can tune for even more sophisticated recurrent neural networks of the type that we'll introduce next week, that it gets a little unwieldy. And it turns out a lot of the things don't matter that much, but each can kind of give you a little bit of a boost in many cases. So do you have 3 layers? Do you have 4 layers? What's the dimensionality of all the layers? And then there are various different kinds of connections and short circuit connections. We'll introduce some of these, but in general, this is like a pretty decent model. And we'll eventually abstract away from how we compute that hidden state. And that will be a more complex kind of cell type that we'll introduce next Tuesday. Do we have one more question? All right, so now how do we evaluate this? It's very important to evaluate your problems correctly, and we actually talked about this before when you have a very imbalanced data set where some of the classes appear very frequently and others are not very frequent. You don't want to use accuracy. In fact, in these kinds of sentences, you'll often observe, I mean, this is like an extreme one where you have a lot of ESEs and DSEs, but in many cases, just content, standard sort of non-sentiment context and words. And so a lot of these are actually O, have no label. And so it's very important to use F1. And we basically had this question also after class, but it's important for all of you to know, because the F1 metric is really one of the most commonly used metrics. And it's essentially just the harmonic mean of precision and recall. Precision is just the true positives divided by true positives plus false positives. And recall is just true positives divided by true positives plus false negatives. And then you have here the harmonic mean of these two numbers. And so intuitively, if you can be very accurate by always saying something or have a very high recall for a certain class, but then if you always miss another class, that would hurt you a lot. And now here's an evaluation that you should also be familiar with, where basically, this is something I would like to see in a lot of your project reports too, is you analyze the various hyperparameters that you have. And so one thing they found here is they have 2 different data set sizes that they train on. And in many cases, if you train with more data, you basically do better. But then also, it's not always the case that more layers, so this is the depth that we had here, the number L for all these different layers. It's not always the case that more layers are better. In fact, here, the highest performance they get is with 3 layers instead of 4 or 5. All right, so let's recap. Recurrent neural networks, best deep learning model family that you'll learn about in this class. Training them can be very hard. Fortunately, you understand backpropagation now. You can gain an intuition of why that might be the case. We'll, in the next lecture, extend them with some much more powerful models called gated recurrent units, or LSTMs. And those are the models you'll see all over the place in all the state-of-the-art models these days. All right, thank you.